Hello, I'm Vijay Gill. I work for AOL Time Warner, and here's my information up top. The Vijay Gill 9 is actually my actual email address, because when I first started roaming a lot within the country and internationally, I always used to carry a couple of AOL CDs with me, and whenever I needed modem access, I would register for a free 1,000-hour AOL account. And I started using Vijay Gill 1, 2, 3, 4, and then I ended up working for AOL, and I got the next available name is Vijay Gill 9, which leads me to say, don't burn your bridges till you come to them. So who's this talk targeted at? Mostly it is targeted at vendors of IP equipment that are used in ISPs today, all three of them, I guess. Because the telecom meltdown happened, and that was bad. We went from, damn it, how many more core router startups there can be in 1999, Dave Cooper from Global Crossing, to 2001. The unemployment office only gives money, not options. So this entire, the subject of the stock has suddenly, the space that the stock is targeted at has suddenly reduced to 5 people. However, they're still ISPs, and we can work, the ISPs can work together to give feedback to the vendors on what we like to see, and there are some things that I will bring up as we go. What the problems are with their networks. Networks cost a lot to run. And with the new environment, we need to reduce on capital and, more importantly, OpEx, because while capital seems to follow Moore's law that you double your processing power and bandwidth every 2 to 4 years, the OpEx, the human people, seem to become more and more expensive every so often. And then security. We saw Marcus give a talk this morning about some of the things that the government is doing to help harden our infrastructure, and we definitely need to look into that, because currently our infrastructure as a whole is completely vulnerable. And I'm not talking about like subverting BGP or subverting the protocol itself. I'm just talking about knocking the routers offline. So here are some slides. These are from last month from AOL NOC, which is the network NOC, and you will see the biggest large number of tickets are routers and switches as compared to the hardware side. And there are a lot more hardware on the host side than there are routers in AOL. So here's a normalized view of our incident ratio. And you will see that the worst router vendor is at 35%. That is about 35% of our installed base has issues that we need to touch every month. And the best one is around 8%. This is compared to the hosts, which we have a lot more of. The worst host that we have, the worst vendor for hosts, at AOL, is around 1.41% incident ratio. So this shows that we have about an order of magnitude to go on our improving our routers before they can match the stability of our hosts. And our hosts aren't very stable, at least according to most of the system admins I talk to on a daily basis. So basically what the problem is that we can only squeeze costs so far. And bandwidth and hardware costs are more elastic because they, I hate to use the word optronics, but I will use optronics. So optronics seem to go about double in capacity every 2 years for half the price. But the human cost, unfortunately, does not. So what we need to do is we need to reduce the incident ratio of our routers, because every time we touch the routers, it costs us money. So here are the top router issues. As we can see, tracebacks and card blade errors account for a significant chunk of our incident ratio. Here's a normalized view of the same data. Incident ratios of 1 to 4 are not good. It means 1 out of every 4 devices every month has to be touched. That's money going down the drain. So what are the resolutions? We see the card blades down, and obviously replace equipment in almost every case. This replacing equipment means we have to send out hands and eyes, remote hands. Each remote hand incident costs money. Here's our ticket versus monitored assets ratio normalized. Some vendors are good, 1 to 8. Some vendors are bad, 1 to 3. And here is our assignment. Out of all the tickets opened last month, 220 of them went to Internet Engineering, which is the group I am in. And so every ticket that goes to the group costs us money. And here are the major cost per bit components of our network. The SG&A is, of course, normalized for obvious reasons, and we are not going to give you the exact numbers here. But here is the trend. Notice the trend only goes to 2001 because that's the last year we have data for. We haven't done the financials for this year. You can see the cost of an STM1, it's normalized to STM1, go down on this very steep curve. And I think at this point we are probably below what the cost to manufacture is. However, our SG&A seems to not go down much at all. Oops. So basically what this means is this gap here between SG&A, this is the gap we need to squeeze if you want to stay in business. This gap right here. And unfortunately, till our vendors make better hardware and have more robust software, we're not going to get there. We used to have this luxury of selling a dollar bill for 70 cents. No longer that does not work. As we have discovered, unfortunately to our detriment, that losing money on every sale and making it up in volume is a joke, not a business plan. That sucked. So basically, that was the cost component. What we're trying to show you is that we do track our costs. We know where the problems are. We know where the vendors with problems are, and we take steps to migrate away from those vendors because they cost us money. So now, that having said, let's talk to our general hardware requirements. One thing we found very useful in operational network is that we would like to see all line cards have power metering on interfaces. And this goes back to all the ISPs here, that every time a vendor comes to you and tries to sell you a new hardware box, a new line card, ask for light level metering. It's not hard, it helps the NOC immensely. You don't get paged. Not getting paged is good. Protect the flash cards. With the popularity of like cameras, we are seeing flash cards start to walk out of exchanges. It's not that hard to put a little clip on so that the flash card is not visibly sitting out there with a big button that says push to eject. The other thing, which is, I suspect most of this is already available, but we've never seen in exposed interfaces, high watermark the queues. The exponentially weighted moving average, that is the so-called the 5-minute gauge, is essentially a random number for microbursts. Because microbursts result in congestion, by the time the exponentially weighted moving average catches up, the congestion is gone. And this is, Sprint had a very good paper on this, Christo Diot, talk to Dave Meyer if you want to know more about it. But the problem that we've seen is the microbursts happen if your access speed is on the same level as your backbone speed. And I don't know about most people, but the AOL data centers are all connected at OC 192 to the backbone. So the chances of having microbursts which show up as dropped users, dropped packets, and don't show up on our exponentially weighted moving average graphs are high. We want to get away from that so we can track if there are certain anomalies happening in our network. Basically, we want more visibility into what our queue depths look like. And of course, working counters, which I know apparently seems to be too much to ask, because we've been asking for them at least since when I was at UUNet in 1998, and we haven't seen anything happen since then. So this is not an afterthought. We bill people on this. And as we've seen, there are like fewer and fewer people left to bill. So the few people that are left to bill would like to have working counters before we go away too. Thank you. Okay, so control point. By the way, I tend to run through these things pretty fast. So if there are any questions, interrupt me. So in the bad old days, at a large, now bankrupt local ISP, we used to see on average about 2 parity-related crashes a day in hardware. This is the infamous PMPE, which I'm sure most of you are familiar with. So basically the thought is, if it does not have, well, the resolution for that, the PMPE was, if it happens again, swap the processor, which is not a way to run a business. So basically the stand that we have taken and that which you should take also is that if the control plane does not have ECC, which is error correcting code on the memory, do not buy the box. And for HEDN, if it does not have ECC on the control plane, we will not buy a box. Done. The other thing is prioritizing hellos. A lot of people have come to us with dual processor boxes. One is the master processor, and then we have a slave processor, and in case the master processor fails, the slave initiates a takeover. So far so good, except that for the most part, they don't prioritize the heartbeat hellos. And what we've seen before in other previous large bankrupt ISPs is that sometimes what happens is when your time diameter of your network exceeds your hold down timers in your, say, I use the word OSPF because most frame relay networks run OSPF. What happens is that your primary CPU is sitting there calculating the SPF tree in case of a interface failure. So you sit there, recalculate your entire OSPF database, walk your database, and recalculate the new tree. Of course, what that happens is because your time diameter is so large now that your CPU is busy churning, it cannot respond to hellos. So the slave sends a hello, the CPU is busy calculating, nothing comes back. Second hello, third hello. The slave says, oh, the primary is down. I will now initiate a takeover. So what it does is it initiates a takeover because the primary is too busy calculating and can't respond. That causes the entire box to essentially do a reset, sending out another flood of LSAs saying that this box is now out, please recalculate. And then the secondary slave starts recalculating its SPF tree, and then the primary sits there and says, ping, I can ping you, ping, ping, I will initiate a takeover. This is not an apocryphal story. This actually happened and took down a very large frame network for several days before we could figure out what the hell was going on. So my feedback to vendors is, please, for the love of God, prioritize your hellos. This is apparently harder than you think because some people have not built in priority queuing onto the hardware. The other thing is, of course, that prioritize IGP hellos over LSA. This is a point brought up by Dave Ward at Cisco, because I don't care if my calculation takes 50 milliseconds or 100 milliseconds longer. I want to ensure that my adjacencies do not go down. So for the vendors that don't know this, please prioritize your hellos over your LSAs. That is, if possible, split the process up into a time-sliced, preemptively sliced hello maintenance and adjacency maintenance process and a back-end database calculator. We don't care how long the database calculator will take. We can live with micro loops. That's what IPTTL document is for. Well, except for the MPLS guys. But we can't live with self-reinforcing oscillatory behavior, which will happen if your adjacencies keep dropping because you're busy calculating your LSAs. And of course, implement back off on the SPF calculation because we don't want to overload the CPUs. So far so good. How are we doing in time? Excellent. So convergence speed. Now there's some effort in the IETF to define convergence speed as basically when the rib has converged, which is, I believe, incorrect because in real world what you really want to do is your convergence speed is predicated upon when you actually start forwarding packets. My voice over IP calls don't care that my rib has converged. They only care when they can actually get their packets to their destination. So this includes things like fib updating. And apparently, naive implementations that we've seen actually sit there and map the entire prefix set per prefix to an outgoing interface. You have this entire database that says, here's my NLRI, here's my prefixes, here's an outgoing next hop. So what happens when, say, a UUNet or a sprint link peer goes down? And these happen all the time. So now you have to take that entire 30,000, 40,000 route set, in the fib and implement each individual prefix for the new outgoing interface. From interface 1, it's now going to interface 6. So you walk 40,000 prefixes and update them individually one at a time. This takes on the order of several minutes. That I define as bad convergence, even though the web has converged in the order of minutes. So a simple thing like putting in an indirect next hop. So instead of mapping prefix to outgoing interface, map prefix to a pointer and then move the pointer and map the pointer to the outgoing interface. So in case you lose an interface, you just update the indirect next hop from, say, interface 1 to interface 8, and all the 40,000 ribs, the routes in the rib that you have that point to interface 1 will now automatically point to interface 8. Again, not rocket science, but you will be surprised at how many people don't do this. And this cuts into our convergence times. Another thing is jitter the protocols. There are several papers out on this, I believe one by Van Jacobson and I forget the other, Sally Floyd, which actually goes through the mathematical analysis of why you need to jitter the protocols. We've seen this before where every 30 minutes or so there's a big CPU spike because all your OSPF processes and BGP, LSA, BGP processes kick off their maintenance timers. And so you basically flood another copy of the LSA database out. So jitter them, so when you start the router, just add some entropy into the timer so they're 25, 30 milliseconds staggered. Okay, this is another equal cost multipath. We don't want per packet load sharing because that normally tends to lead into packet reordering, although some of our routers do it for free. What we're asking is, assuming you do this, you do a source destination port hash. I mean, I'm just using this as an example, it doesn't matter. As long as you have a deterministic hashing system to split your interface load between your outgoing interfaces. And this is the AOL, some of the AOL data center and backbone component in Northern Virginia. All the backbone links are OC192, everything else is OC192 or OC48. What happens is when you do a deterministic load split, the router, in the first router in the load, in the path, splits the traffic, half goes to one parallel interface, the other half goes to the other interface. And now the router above that, which is aggregating all the traffic, gets all this deterministic, already split traffic coming in, and then it tries to do a deterministic hash as well. Of course, by this time, your previous routers have already eaten up half your hash space. If a packet matches hash A sent to interface 1, matches hash B sent to interface 2. There are no other choices. And every router that is sitting on interface B, upstream of interface B, now only gets packets that match to hash B. There's no other choice. So as I've taken an example of a hot 192. You will see both of these 192s go to two separate routers, and one of them is running hot, and one of them is not. This is because our vendor had an ECMP bug, which was basically not randomly salting the hash algorithm. So when these OC192s started splitting traffic up here and up here, I'll illustrate from here they go up. This router does the exact same split. So now all the traffic that came up the lower half of the hash now goes to this router, and you've seen the line starts to heat up here, and then this router takes all these aggregated 192s and then splits them all across this link. Oops. So what we're asking is randomly salt using a good source of entropy. Due to maintenance procedures, most routers in an area or a cluster tend to be rebooted very quickly, one after the other. And if you're basing your hash on timer since reboot, sometimes they will not do the right thing. So we are asking, pick a good source of entropy, I don't know what it is, maybe a small cesium detector. Another thing is traffic matrix. Sean Duran actually had a really good idea. This was like, we were arguing about it on NANOG 2-3 years ago. And he basically said what became Ceph prefix accounting. Map every prefix to a next hop and then associate a counter with that next hop. So when you send traffic to that next hop, increment the counter. You will get a router-to-router traffic matrix that you can use for your TMS, your traffic management and statistics. Unfortunately, this does not seem to be most vendors' strong point. And what I'm saying is, how can you do proper capacity planning without either running MPLS edge to edge or POP to POP to get good statistics, or running NetFlow on the backbone interfaces? And running NetFlow on backbone interfaces is hard. Trust me, it costs a lot of money to upgrade your engine N to N+1 so you can actually run NetFlow on. And we need BGP, next hop, router to router flow so we can actually capacity plan properly. Please push this whenever you talk to a vendor, push traffic management statistics on them so we can actually get working networks. Second part is security. I'll go a little bit faster here because I'm running out of time. Move all your console ribs, the console out of band, to a separate rib. I do not want any way ever for in-band access to my out-of-band management ports. I mean, this should not even be turned on even if you want to. This is bad because once they get on my out-of-band, they have essentially console access to my all my network devices, including my hosts. This is not something we feel good with. Packet filtering should work at line rate, at 40 bytes, not iMix traffic, because the reason we don't want iMix traffic is we don't know what's coming 2 years down the pike. If we had planned for FTP and NNTP, which were the dominant traffic flows in early 90s, late 80s, we would have not been able to take care of the World Wide Web. Because we don't know what's coming 2 years down the road, so I don't care what iMix looks like today. I want to know what iMix looks like 2 years from now. And if I did, I wouldn't be talking here, I'd be sitting in the Bahamas. Also, real output packet filters. Inverting and applying to all incoming interfaces is not useful because sometimes we apply these on our core routers and they transit traffic. We do not want our transit traffic to be blocked by an outgoing interface list. So this leads back to the original problem I was trying to solve or talk about, which is that our routers are vulnerable. You can knock down pretty much any router on the internet today by directing a few megabits of packet per second to the router. And the problem is that routers are optimized for taking traffic in and passing traffic out. They're not optimized for taking traffic in and then processing the traffic. That is, routers tend to process data and move it around from interface to interface as opposed to digesting or generating data. Routers do very poorly at that, and the problem is that there's no cost-effective, economical way to build a router that can take, for example, an 8-port OC192, 8 gigs worth of traffic, 10 gigs worth of traffic to the route processor. Sorry, 80 gigs worth of traffic. If you can do that, it'll cost a lot of money. Essentially, you've doubled your router port cost because you need to have the same high-speed serial links and lots of CPU to digest all that traffic. So what this means is that no matter how big your routers are, all somebody needs to do is send enough traffic to overwhelm the CPU. This is the weak point. Oops. So the first step at solving this issue is that something, again, which looks to be simple, but most people do not pay attention to and do not have, and I ask you as ISPs to push your vendors to do this. I want simple, unambiguous parsing. Filter stuff for the router, the to-us traffic. If traffic comes to the router, I want a simple way to disambiguate interesting traffic from uninteresting traffic. That's the first step, and nobody can really do it today. Packets come in, they all go into the queue, they all go to the RP, and they rely on the route processor to disambiguate good from bad, which is, of course, completely useless if you're being hit with a packet flood. You're so busy disambiguating good from bad that you're going to die. So this should be done on the line card because then you've distributed your processing load over multiple interfaces as opposed to a single choke point. So we've seen DOS stacks targeted hardware. They're increasing. And rate limiting is not an answer because you can always send enough fake BGP packets to the router that you will knock down valid BGP sessions as well. And that causes instability. IGP traffic can be safely blocked unless you're PSI net, I guess. You're not running USPF with any of your customers, hopefully. So basically what we want is short-term dynamically filter Oh, by the way, MD5 is not an answer because you can always send enough fake MD5 that the router will crash anyway. And ideally, what I really want is we want to move the control plane out of band, in band, so to speak, as in like run IPsec or something tunnels and then run the control plane on top of that. Unfortunately, to do any of this, vendors have to implement priority queuing for control traffic. So I'm going to run through this. This is essentially something that Juniper has done, which is basically update your filters dynamically whenever you configure a BGP peer, so that at least the attack space is reduced. And one thing to the feedback for vendors is please ensure that your TCP/IP stack chooses randomly when picking a source port. Currently, most do not, so I can easily knock down a router even with a Hoopo filter. If I start from 10,024 and continue till about 6,000, I will run into the right port. This is bad. Use the same entropy pool that you pull for your ISN randomizers. And I know most router vendors have good ISN randomizers. Use the same thing for your ports. There's also another security issue, basically, that we've put out. This is the BGP TTL security hack, which basically inverts your BGP algorithm. And instead of sending TTL1, so you can talk to your directly connected neighbors, we set the TTL to 255, and then only care about IBGP or BGP packets that come in with a TTL of, say, 254 or 255 or 253, and minus multi-hops, of course. I'm completely out of time, so you'll have to go to this URL. Okay. Go to this URL and run it. This also assumes that you have working line card filters, so you can filter on your IBGP source addresses coming from outside. Because if you can't filter your IBGP source addresses, this doesn't help you at all. And that's it. Sorry for running a bit quickly, but any questions? Any hate? Uh-oh. Hey, Woody.
Usually the convergence draft you're referring to in the benchmarking specifically states it's not, that it's only doing, the convergence definition is only for one part, and that the whole part, at least it should be, as I'm one of the authors, and I'll go back and check, but the whole part is the convergence on the control plane plus getting it to the forwarding plane, but it was breaking it apart for benchmarking. So if that's the draft you're referring to in your convergence document, it's trying to say, no, we're not the whole part.
Okay.
Which is part.
Thank you. Any other questions? All right. Thank you.